Hello, how's everyone doing? Long time no see. Today we're going to look at this paper called Scaling LLM Test Time Compute Optimally Can Be More Effective Than Scaling Model Parameters. This is a collaboration by Google DeepMind and UC Berkeley and explores the question of how can you invest flops at test time to get good results out of large language models. So this is specific to large language models. Maybe not though, but they experiment on large language models. So you have your LLM and it can produce text, right? Given some prompt. Now you have a specific task that you're looking at. In this case, they are going to look at a benchmark called math, which is high school math questions of various difficulties. So it could be, little problem formulations, or in the simplest case, like 1 + 1 or something like this equals, and then you put this as a prompt and you want the LLM to output the answer right here. So 2, debatably, but let's just assume that it's 2 for now. Then the question is, as these problems get harder, obviously the LLMs will get worse and worse at doing them, or getting the right answer often. If you have some extra compute at test time, so not at training time, but at test time, how could you use it in order to make the final answer that your system gives better? So I can give you one example. Let's just say we just sample a whole bunch of times. We sample 20 answers from the same prompt, and then we just output the one that is most frequent, right? So this is an easy way, let's say, of hopefully improving the output. So if you assume your LLM does anything useful at all, then this should improve the output. Otherwise, all you do is just reduce variance. But there are other things. You could do chain of thought prompting or something like this, right? You could put a prompt like, hey, you're a very good math, person, come up with a plan, and so on. And then the LLM outputs a plan of what to do. And then you give the plan back to the LLM and say, oh, hey, here's the plan, right? Why don't you solve this problem using the plan? Output your thoughts and what. Like all these prompting techniques, they're essentially also just a way to invest extra compute at test time in order to make the whole system give a better answer. So this paper explores a bit more systematically how to invest extra compute at test time, and they look at a bunch of stuff. Now, this is the good part is really that they do a lot of thorough experiments and report the results and lay out pretty much everything. Especially also the appendix is quite large and has a number of extra experiments in there and so on. On the other hand, I do think they are trying a bit too hard to come up with sort of general rules extracted out of their research that in my personal opinion, probably, if I had to guess, probably will not generalize super well to other problems, other domains, or even other benchmark data sets rather than this math data set. But still, it is interesting to see what they're doing, how they're going about it. And yeah, also the notion of compute optimality that they're bringing in. So what they're essentially going to do is they're essentially going to say, we're trying a bunch of stuff and we'll tell you how well the stuff worked, so that if you are in this situation, you can choose the good stuff based on what our recommendation, right? How much this is, concurs with the notion of any sort of optimality is if you really define it well, yes, they allocate compute optimally according to their own constraints. But other than that, the paper is rather, we tried a bunch of stuff and we'll tell you how well it worked. Okay, so with that, I'm sorry for being a bit down here. Let's dive into it. They need a bunch of stuff in order to even start this research. So they need two things. One, they call let's say, a verifier. So a verifier you may also know as a reward model, a value model, value network, or anything like this. So the verifier, you have your problem statement, right, of the benchmark, and you have your correct answer. So this is your whatever X, and then this is your Y star, if you will, the correct answer. Now, your system is going to do something here. 1 prompt, 2 prompts, chain of thought, whatever. It's going to come up with some sort of answer. And the question is, you get a point if these two match or are somehow the same in some notion of the sameness. In this case, it's really if they match, because the output is like a math output. You can verify that quite easily. The verifier is a model that's trained to estimate this thing right here, this sameness. So it gets the question, it gets the answer, and it is trying to guess whether that answer is the correct answer for the question. Why would someone do that? Because history has shown that it is easier for a model to judge whether an answer is correct or not than to produce a correct answer. So the verifier here is going to play a crucial role in some of this research. Specifically, what we're going to use here are what they call them PRM, I think, in the paper. So these are called process-based reward models. So they not only take into account the input and output right here, they also take into account at least parts of the way that this answer was derived. And they can even score partial things. So let's say you have your input and you are somewhere in between. So you're somewhere in your reasoning, you output the first answer, now you're trying to come up with a better answer, and so on. So you can even give it sort of a half-finished solution, and it will still come up with some sort of value for it. So the verifier model here, the process-based reward model, is going to tell you, yes, this looks like it's on the right track. Or if it doesn't, then this doesn't look like it's on the right track. So this is the verifier model. They're going to train a verifier model specifically on this math data set. We can look a little bit into how they do that, but this is almost like a precondition already to their work. So as a precondition, they have to have a verifier model to do some of what they do later. And also, they're going to need a model that does answer refinement, let's say. So in essence, right, you can just train a model to take X and, produce Y. And yeah, you can prompt an LLM, you can even train an LLM to do that, and so on. But in order to do some of their techniques, they're going to need multi-step problem solving, let's say. So what they're going to train is they're going to take an LLM and they're going to fine-tune it specifically on this data set for iterative refinement of an answer. Meaning, you put in X, the LLM, you prompted like, hey, here's a math question, give me the answer, or whatever. It comes up with Y1. Then you give X and Y1 to the model, it comes up with Y2. Then you give X, Y1, and Y2 to the model, it comes up with Y3, with the idea that each successive step here is a refinement that makes the answer even better than the one before. Right? So you can see how these two things are going to interplay. If we have by the way, you could also achieve this by prompting sometimes, right? Depends on the model and the problem, but you could just say, hey, look, here is an answer and here's the first few tries at answering it. Please come up with an even better answer. But what they're going to do is they're going to fine-tune a model to do this, as they're also going to fine-tune one of these reward models. So you can see how these play together. Like you can produce the first few answers in this chain, then give them to the process-based reward model to figure out whether you're on a good track or not. And you're already kind of seeing ahead that one method they're going to try in terms of test time compute is, hey, let's do something like a tree search or a beam search, where I'm going to start with, the first answer right here, and then I'm going to refine it into a bunch of different, so y2a, y2b, y2c, up until y2k, haha. And then, from here, you're going to score each one of these paths by themselves and decide which one to continue with, and so on. So again, the verifier and the model that is able to refine answers, these are both preconditions to their research, which does make their research kind of intricate, and which does make all the results strictly dependent on how exactly they trained these models, because you have to interpret all of the results in light of the fact that they have had to fine-tune the ingredients of the research, and that they have done it in a very particular way. So keep that in mind as we go through these things. They're going to make here a kind of a taxonomy. So they're going to say, okay, we have some flops, and now there are two ways. They want to give a unified perspective on test time computation, and they're saying, oh, what you want to do is you want to modify the model's predicted distribution adaptively at test time, right? And you can do that in two ways. There are two knobs to introduce modifications to an LLM's distribution. At the input level, meaning you can change the prompt, add some tokens or whatnot, or at the output level, for example, by sampling multiple candidates from the standard language model and performing surgery on these candidates. So we can either modify the proposal distribution, or we can use some post hoc verifiers or scorers in order to do that. And while I generally agree with this taxonomy, if you will, I don't think it's so clear cut. So again, rather interpret this paper as we tried a bunch of stuff, because for some of the scoring methods, right, they're going to need these input modifiers. And what I mean specifically is something like beam search, right? Beam search, you could say, well, we produce multiple results and then we select among them which one is the best. But in order to do beam search, you actually need a multi-step process. So yeah, they're not so independent as they make that seem here. And yeah, they're trying to say something global where it's just a bunch of different methods. So we're going to skip over a lot of this taxonomization and categorization and systematization. I do want to point out this, where here they say, what we're actually after, in general, we would like to select the optimal allocation of our test time compute budget for a given problem. So we define the test time compute optimal scaling strategy as the strategy that chooses hyperparameters corresponding to a given test time strategy for maximal performance benefits on a given prompt at test time. Formally, and now they're going to formalize this. So they're going to say, this here is the test time compute optimal strategy, right? So this is a set of hyperparameters that decide where you allocate your flops, given a prompt here and given a problem statement. Probably a problem statement. I'm not sure what the A star is. Yada, yada, yada. Da, da, da. Da, da, da. In any case, you also have a budget here. This is the argmax of the expected value of sampling the output according to the distribution induced by the hyperparameters and the budget and the prompt, obviously, over whenever these indicator function holds. The indicator function holds whenever you get the correct answer, like whenever your answer is correct. So whenever your answer is the correct answer for the given prompt. This formula right here, as far as I can tell, is, except for here, never referred to again. Nothing is derived from it. I may have overseen something in the appendix because I didn't look at that hyper closely, but nothing is done with it. Nothing is derived from it. It is not used to make any other arguments. It's just here, like it's just here. So there's math in the paper. And that, to me, I get it. If you want to submit it somewhere, you have to do that. But it just seems a bit unnecessary. Like if I told you, look, we can do a bunch of different things at test time. What we want to find out is, you give me a prompt, you give me a budget. Can I tell you, for this particular situation, what the best thing to do is? Is it beam search? Is it chain of thought? And so on. Like, could I tell you, just looking at the prompt and the budget you have, what you should do? Right? Isn't that much more understandable than this? Especially if you don't do anything with it, right? That's the issue with math. Like, you formalize because then you can do stuff with it, but they don't. Okay, rant over. Let's dive in. The first thing they do is they, let's skip over all of that. They look at this output distribution modification. So let's say we have a bunch of flops available at test time, more than is needed to just sample a different answer, or sample one answer, right? Maybe we have budget to sample a bunch of times from the LLM. Well, what could we do? The easiest that we could do is this, what they call best of n. We could just sample a bunch of times. And then, well, for one, we could just use the majority answer. But if we have a verifier model, right, a reward model, we could use the reward model to decide which one of those is actually the best according to the reward model. And that's what we can output. Okay? Pretty simple, pretty straightforward. Sample a bunch of times, score it. Then beam search and look ahead search make use of a model that refines its own answers. Right? Now, again, this is fundamentally, like, it requires one more ingredient, mainly a model capable of doing that. And it is no longer just modifying the output distribution, right? So the categorization, in my opinion, does break down already here a little bit, except if I misunderstood something fundamental here. But okay, you're going to have a question. You're going to sample 4 answers like in best of n. You're going to score each of those answers like in best of n, but then you don't stop. You actually continue from the best couple of answers, not just one, but best couple of answers. So 2 answers, for example, here. And from them, you're going to trigger the LLM to refine the answer, right? And again, you're going to end up with a bunch of answers. You look at each of them again, which ones are the best, okay? Pick the 2 best ones. And again, go ahead and from those, sample another refinement. Now, what is obviously, for the same budget, you can obviously have much more answers in the first case, because in the second case, you actually need to save some of that budget for going down the tree. So it's a trade-off between, diversity, essentially, like sampling a bunch of times, and between iterative refinement from a good starting place. So this is the combination here is in the form of beam search. And yeah, you can see this is a possibility. And then the last thing is look ahead search. Now, as you can see, the methods get kind of progressively more complex as you move to the right. So you invest more and more into like single individual steps. So you have to manage your budget essentially better. You're going to take a question. Again, sample a bunch of times, like in best of n, like in beam search, but now you don't just pick the best one of these answers, but what you're going to do is you're going to do like a fictitious rollout into the future. This is very reminiscent of kind of Monte Carlo tree search. If you've seen like AlphaZero or something like this, this is very reminiscent of those. So you're going to fictitiously use your LLM to roll out into the future. So you do a rollout, which just means you refine a bunch of times the answer. So you just tell the LLM, I don't know, refine it 3 times or something, improve. You do that from each of these answers, right? You're going to end up with 4 hypothetical future states given the corresponding beginning states. And what you're going to do is you're going to score the future states. So you're going to score these things, and whichever ones of those turn out well, those are the original answers that you're going to take into the next step. So it's like beam search, except the scoring step is not just the verifier scoring the answer, but it involves an inner rollout into the future to score, but then you don't take the result of that rollout as the next step. You actually go back to the original one. This is very, like in beam search, you already have to decide, well, how wide, how deep, and so on. Look ahead search, this is even more complex, right? You have to decide, how wide, how deep, how far is the look ahead. And by the way, if your model isn't good, then the look ahead might even hurt, right? You refine your answer a bunch of times if there's some noise in that process, because you don't, like AlphaZero will actually do a tree rollout. Like it will roll out a bunch of times, different times from a given state, and that's how it kind of does the search. This here, it rolls out one, as far as I can see. It just rolls out one path up into a certain depth, and then it uses that to score. That is an incredibly, or can be an incredibly noisy way of doing things, but potentially it's more accurate, right? Because you don't score the now, you score what could be. Okay, so these are the methods they're investigating first, and here are the results. Now, let's pick a color that's not here. Maybe this one. No, that's here. Oh well. We'll go with red. You can see that in general, the look-aheads underperform. So the green line here is the majority. So the green line is the only one that doesn't make use of any verifier model, and is pretty respectable. So down here is the performance if you just ask the LLM for the answer on this math benchmark. And then as you get more generation budget, you go here to the right on the x-axis. You can see this majority voting. You just sample, for example, here 2 to the 5 times, and then you take the majority, and that already gets you pretty far. So this isn't too bad for this. You can do with like a pure LLM, nothing else. You don't need a verifier, you don't need a reward model, you don't need refinement fine-tuning or anything like this, or special prompting. You can just do that. You can just, if you have 10 times as much budget as for a single answer as the answer costs, just do that. It's probably even easier with now prompt caching being so pervasive. Like it will probably not even, it'll probably be very cost effective to do that. I'm not sure if the prompt caching also applies if you do it in parallel, because the latency might suffer a bit, because usually you could do this even in parallel, right? You can just sample 20 things in parallel and then do the majority. All right, the orange one is this best of n weighted. So that's when you have a verifier. Do the same thing, sample a bunch of times, but then use the verifier in order to decide which one is best. You kind of weight it, aggregate according to its score. And that, you can see, does perform, a bit, quite a bit. It does perform better. Does outperform going up here. And you can see that the look-ahead methods, they underperform here. So they're not going to look at these look-ahead methods anymore. They're just going to say, well, they obviously are not they're not outperforming even the best of n weighted baseline. So we're just not going to look at them anymore. However, the beam search ones, they have a bit of a bump here. So they have a bit of a bump in this region, but then not anymore. They kind of track the orange line up here. These are just two different settings of beam search. Now, they're going to argue here a bit, given this bump. Right? They're going to say, hey, this bump, this means something. And what I want you to look at is this region right here, right? So this, it goes up and then goes down again, right? Why would it go down again? Like, I get that it sometimes flattens out, right? But why would it, like, the red one even goes down and the blue one, it goes slightly down, I guess. But even if it weren't, it kind of flattens and then accelerates again to here. Like, why? If you invest more compute, strictly, you should get better with any of these methods if your like verifier model is better than random, and if your LLM is better than random. So if they do anything at all, you should get better with increasing compute, and your shape should kind of be consistent. Like the majority voting shape here, it's quite consistent. The orange one here, it is quite consistent, right? But the beam search one isn't. So what you're left with is saying, well, it's probably noise, right? It's a property of the data set, a property of the models. Just, this compute budget just gets itself into some sort of nook, and so a couple of these answers come out wrong. That's fine. Noise is totally fine. However, if this, now look, if this here essentially is like the scale of noise that you have to calculate with, then all of a sudden, this difference here between the orange and the red line isn't such a, in my opinion, isn't such a difference anymore. So, and some people will say, well, but it's both of the beam searches that are higher. Well, these clearly seem to be correlated. They both have that dip in this region. So they're not independent runs of beam search for some reason, right? So the multiple lines do this trick isn't going to work here. So again, like, I'm not opposed to finding that beam search does better in some regions and so on. I'm just saying this is the level of noise that this plot suggests. And in light of this, the difference here on the left is not as different of a difference anymore as initially seems if you just look at the plot without anything, without any error bars that aren't there and things like that. Okay. They're also going to divide up the dataset by what they call difficulty. So the dataset already has a notion of difficulty. However, they say that did not work for us, which is interesting, because it does mean that apparently what it seems difficult for, let's say, humans, or in some way of scoring difficulty, might not be the same as difficult from the perspective of an LLM. So the way they decide on difficulty is they just ask an LLM to answer the question a whole bunch of times, and then they either use the correct answer or the verifier to see how often the LLM got it right. And if it got it right, so you're right, you have your X example a whole bunch of times, and then you just count how many were right, either according to the oracle or according to the verifier, and that determines difficulty. The more times the LLM got it right, the easier the question is. This compute to determine the difficulty is not part of any flop estimations and so on. They just see this kind of as a given. But it's interesting that this form of doing difficulty, is just different from what the data set had, meaning that, LLM difficulty is its own thing. And it also means that these things, let's use metaphors that you shouldn't use right now, but these things think differently. They think in their own way, at least as of now. Okay, so they divide this up by difficulty bins, and inside of each bin, this x-axis here is the same x-axis as the x-axis here. So as you go to the right, the compute budget gets larger. They're also going to make some statements here, namely the statements are such as on the easier problems, beam search shows sign of over-optimization with higher budgets, whereas best of n does not. On the medium difficulty problems, we see beam search demonstrating consistent improvements over best of n. So green here being majority, orange being best of n, and blue being beam search. So they say, okay, beam search might have some troubles if you give it more compute budget. You can faintly see here behind that even majority is beating beam search, and also the orange, the best of n, is beating beam search. Also here at the higher compute budget, it's beating the beam search. And it does so more as you give it more compute budget. So they say this is over optimization, which is a thing that can happen if you have a reward model and you give lots of compute to a process that optimizes that reward model. The process is eventually just going to find properties of the reward model, like exploits, or you call it, of the reward model, that have essentially nothing to do with the real problems. It's just a property of exploiting the reward model. So they say that might be happening here. However, as you increase the difficulty level, that no longer happens as much, and you can see the finally beam search being more outperforming the best of n weighted. Again, I would draw your attention just to the kind of irregularity and level of noise that you see in these plots, right? And for example, here, this seems to be a quirk, and that's fine. Again, if that's noise, that's totally fine, but that does indicate to us the level of noise present in these problems, in these solutions, in these processes, which then you have to overlay that level of noise, which presumably is at least something like yay big. You have to overlay that onto things. And again, at that point is less clear kind of what's better, what's worse, and what are the trends, right, among these things. I do feel like there is obviously a consistent trend on more difficult questions. The general scores go down. But again, I want to draw attention to your fact that they say, well, the dataset difficulty didn't do the trick for us, meaning probably they didn't get any sort of regularity in their data like you see them here, like these statements they can make. Oh, at lower difficulty and higher compute, beam search does this, but then it does that. I'm going to guess, and I guess they implicitly say that when they use the datasets notion of difficulty, that probably didn't happen. So I'm going to guess they first tried that, and then they came up with this notion of difficulty where they can at least say something about here. So what's the conclusion? The conclusion is essentially there's no one-stop shop. Like, you have to, if you get a problem, if you get one of their problems, you have to determine first its difficulty. Then, right, you have to go look in the appropriate bin. Then you have to see what is your budget. That determines your column right here. And then you can decide by looking at their experiments which one is the most optimal, what's the most optimal thing to do in your particular situation. So this process of even finding the optimal thing to do and then applying that optimal thing depending on your budget and on your question, that is what they call compute optimal allocation. Right, again, it's only compute optimal over the three things they've tried. And already that requires, determining of the difficulty and so on. But still, if they do that, you can see they can kind of retain that bump on this end. So these are now the compute optimal. So these are dynamically chosen strategies. So they can retain that bubble, and at the top end, they can now perform at least as well as the best of n weighted. However, again, given the level of noise, if your generation budget is anywhere here, you're probably fine with best of n weighted. And here, I'll let you be the judge of whether it makes sense to go with best of n. And again, whether or not this generalizes to anything else, it also remains to be seen. I do believe that because of the fact that they have to have very particular fine-tuning models and so on in order to even do this research, it's a high chance that even if you swap out the benchmark and do this on another benchmark, that the results would probably come out at least a little bit different, and that the strategy a bit different. So maybe the paper's lesson is just that there's not really one perfect way of doing things. Depends on your situation, and it may even depend on the individual sample that you have in front of you. All right. Yeah, the statements they're going to make here is something like, we find that we can nearly outperform the best of n using up to 4 times less test compute. So they're going to find the cherry pick the absolute, here versus here, 2 to the 4 versus 2 to the 2. And then they're going to see, oh no, wait, 2 to the 4, 2 to the 6. Oh, this point here is like almost as good as this point here on the green line. And that is a 4x compute difference, right? But, I get it. You want to point out the best thing about the research, but I don't think anyone looking at this graph is, it's a bit of a too general statement that is warranted by the graph. All right. They're going to go on and saying, well, what if we actually change the input to these LLMs? Now, we've already, in my opinion, done that by doing the beam search across, refinements. But they say, well, we can do different things. We can essentially sample in parallel, which is, I guess, what we've been doing in best of n already, or we can actually sample in revision sequence, which is what we've been doing in that beam search thing. But and then we can combine them, right? We can sample a bunch in parallel and then do revisions in parallel. Again, I do believe some of that we've already done in kind of the beam search and so on, but now we're going to investigate explicitly what's kind of a good trade-off between sampling parallel or trying to refine the answer, right? Is there like some sort of optimal way of, is one just better than the other? And turns out they also find something here. Yes, so these are the results. On the x-axis again is on the x-axis is the ratio between sequential and parallel computation. So the further right you go, the further sequential it is. So the more they invest their budget into just producing longer chains of refinements, and the more to the left, the more parallel it is. So the more they invest their budget into just parallel. So on the left, you have the original thing, and then you go wide, but not very deep. And on the right, you have the original thing, and then you go deep, but maybe not very wide. So which one's better? Again, they define by number of generations. So this is kind of compute budget, if you will, according to the color. And the y-axis is the test accuracy. So you can see that there is a sort of a, if I had to draw this, it would sort of be something like this right here. Okay. So it leans towards the sequential. However, it is not a guarantee. It is not that the more sequential you go, the better. If you that's the overall trend, I guess, but you can see that this here is kind of trending up. This here isn't too trending down. This here is also kind of parallel. It's only this top one where the last step really trends down, which I think if you take away that top line from the graph, then it, like, interpreting it the way I did it, where with that arrow I drew, is not as clear anymore. Like, imagine that top line isn't there. I'm not sure if you wouldn't just say, well, clearly you just should go more sequential. They also do some experiment, again, binned by difficulty, and they find that, well, probably here doesn't matter too much. Here also it's probably better on the sequential side. Here there's a trend towards the sequential side. Here there is a downturn again, and here it's probably just this last thing here is down, but then also so is the middle thing. So again, if the middle thing is down so much, I'm not sure you can make a statement about the fact that it goes down here, right? Like, you'd have to explain why it is better here and here in order to make this trend into an argument. But they're going to make that trend into an argument because, well, here you just have one hill, right? But you don't have it here, right? So they're going to make, in my opinion, a weak argument that we see that while increased sequential revisions tend to outperform more parallel compute, at higher generation budgets, there is an ideal ratio that strikes a balance between the two extremes. And then we see that the easier questions attain best performance with full sequential compute. On the harder questions, there is an ideal ratio of sequential to parallel test time compute. Yeah, you decide. And again, they do like compute optimal things where obviously they can get the best out of every world if they always choose the best out of the ones they have available according to their, previous experiments. They do separate those, like they do cross-validation, at least according to the paper. So it's not like they kind of implicitly train on the test set. So at least they generalize to their own data set, which is good, which is a good indicator that that could also be, applicable more widely. And then lastly, they have a notion of kind of trading between training, pre-training, and test time computation. So they're going to ask, well, if we have some extra flops and we had the possibility of deciding whether to invest it into pre-training, more pre-training, or invest it into, test time, where would you put the flops and in what situation? All right, I just made a very shady setup with a power connector. So if this blacks out, excuse me. We're through the bulk of the paper, but it is interesting. So they're asking how could we, use what we learned right here in order to answer this question, right? Should we invest more into pre-training or should we invest more into test time computation? Now, obviously, this is super duper dependent how often you expect to sample from your model, right? If you're a Google or something, it almost doesn't matter how much you spend on pre-training because you're just going to sample from that model a billion times, which any extra compute invested into pre-training is almost nothing. Then if you had to do extra computation at test time, that's multiplied like by a billion. So this is all dependent on, how often you're going to use that model, and they're very aware of that. So they say, the experiments that we're doing right here are all dependent on that ratio. How often do you expect to use it, after you've trained it? So on the left here, as far as I understand, the left here you see model, you see when they expect to use it not very often, I think. And on the right is when they expect to use it very often. Let's read. Let's read to make sure. So lower inference load, r much less than 1, r much less than 1 is the green line. Okay, then we were wrong. So lower inference load is here. In higher inference load. So that's when you sample more often. You expect to sample more often. And that is on the left side. Yes. Okay, so on the left side is, I don't know, Gemini. I'm just using Google as an example. It's going to be exactly the same for OpenAI and whatnot. On the right-hand side is, essentially the researcher who trains a model to like run 1 or 2 experiments, and that's it. You can see the star in this case is the star is where you invest it into the pre-training. So you do have a language model and you invest into pre-training. And that's where for the different budgets, that's where the stars are placed. So the stars are, I have some extra compute and I invest that extra compute into pre-training. So whenever the line here is below this corresponding star at a given location, it means it's better to invest into pre-training. And whenever the line is above the star, like here, it's better to invest into the test time compute. Now, naturally, you're going to find that when you expect to sample less often from your model, it makes more sense to invest into test time compute. When you expect to sample a whole bunch of times from your model, investing into pre-training is much more valuable, because one investment into pre-training will affect all of the inferences, whereas one investment into inference just affects one inference. So that's why naturally you're going to see the stars towards the left being above the general lines, and the stars on the right sometimes being below them, for example, here or here. So it turns out that on easier questions, which are the more purple and red lines right here, on easier questions and in the situation where you don't expect to sample as often, it can be more effective to invest into test time compute rather than pre-training. But in situations where you expect to sample very often, it is almost always better investment to invest into pre-training. This obviously all extremely depends on their assumption of kind of how much worth is a pre-training flop for an inference flop and so on. But yeah, that's essentially, you just have to make a choice, right? You can only say something if you actually put some numbers on something. So that's good. They are going to come to a conclusion, essentially say the star represents the greedy pass-at-one performance of a base model pre-trained with about 14 times more parameters. We plot the test time compute budget on the x-axis. Yeah, place the stars at 3 different locations. So the pre-training, they're going to invest to train a bigger model. Because if you pre-train more, then you can afford a bigger model. So whenever the line here is better than the star, that essentially means that using test time compute, you outperform a model that's 14 times bigger than your model, right? Because if they invest into pre-training, they invest into a 14 times more a bigger model. So yeah, that means that they can now claim that in some situations they can actually, using test time compute investments, they can actually outperform a model that's 14 times bigger than their model just by investing more test time compute in the smaller model. And that's a pretty cool statement. However, this is to be qualified by saying, we see that on the easy questions or in setting with a lower inference load, that test time compute can generally outperform scaling model parameters. However, on the harder questions or in setting with a higher inference load, pre-training is a more effective way to improve performance. And sadly, a lot of our problems tend to be, or a lot of our use cases tend to be either in the higher inference load setting where someone trains a big base model and then lets everyone use it, or the harder questions are obviously naturally more interesting. But if you do have the easier questions and you do only expect to run the model every once in a while, it might be generally a good idea to just not train a bigger model or not invest so much into pre-training, but save some of that money to do test time optimization. Could get you a better result. But it's all that it depends. So you probably have to find out for your particular domain. And I'm afraid that even though the paper tries to sort of pull out general principles out of this research, I am afraid personally my impression is that I would not trust that. I trust this research that they found what they found, but I would not trust this to generalize anywhere beyond like this particular data set, the particular method they have pre-trained their refinement model, which we didn't go in here, but if you're interested, it's actually a pretty cool method that they use, but it is very particular to this data set, right? And so this kind of generating revision data, I like it, but it is very particular, and therefore it is something that heavily influences all the outcome of this research. Also how they trained the verifier, right, is quite, that's a bit more general, but still it kind of narrows down the, it just does something that makes the research dependent on some more of their specific tricks. All in all, cool research, very good that actually someone looks into that, tries out a bunch of different things, reports them back saying, here's what worked, here's what didn't work. I like that very much about the paper. They're very transparent, it seems. Haven't reproduced it, but they're very transparent, at least it appears so. The downsides to the paper, yeah, as I already said, it's probably quite a it depends thing that comes out, and the paper does try to make a bit more general statements given their research than I personally would find warranted. That's it. I hope you enjoyed this review. This paper was part of a paper discussion that we have regularly on our Discord. If you're interested, come and join. It's always a good time, and I'll see you around. Bye-bye.